is complicated. It has a lot of information stashed within it. That information allows you to make lots of conclusions relatively quickly once you've gotten through that literacy threshold of understanding the information that's embedded within it. Right? So you have to be able to deal with that. If you don't like the figure, that's okay. You still have to know all the content that's embedded within the figure. Kind of like the periodic table. You don't have to like the periodic table. You still have to know how to pull information out of it. Make sense? All right. So what this is attempting to do is to establish all of those relationships. Okay. One of the things that needs to get added to this figure that I've not had time to generate, and for the record, when you're making fun of the figure, you are making fun of something that I have created. This is not something that is widely accessible. This is only something that I built. What it needs to have is at the top a full spectrum. Because really what we're talking about is a summary of any interaction between anything, any individual atom interacting with another individual atom. Right? If that interaction is very, very weak, we could call that a force. If it's very, very strong, we can now call that a bond. And that's largely dependent on the ability to share or not share electrons. Okay? It is a spectrum, though, which means there's effectively an arbitrary line somewhere in that spectrum that is the difference between bonds and forces. Okay? That arbitrary line happens to fall right through the ionic bond and the ionic force. They are so closely related as a type of attraction that we could label it as a bond or we could label it as a force, depending on which level of that line we were trying to evaluate.
So that's why you have the dotted line to indicate that flexibility.
Yep. If we look at the entire spectrum goes from weakest to strongest force. So what I did was took that initial bar and just turned it into a nice circle, because circles are more pleasing than, say, if we did a little rectangle like a table. Right? At least to me. Right? So we're taking the weakest attraction, a London dispersion, and we're slowly seeing that gradually increase in strength all the way around the wheel until we get to the nonpolar covalent bond, the strongest attraction. Okay? Why throw in the color coding? Because this color coding would almost make it look like it's two separate things. Well, if I have a London dispersion force, that means the atoms from that attraction, so if we break this down with two directions, if I take a look at atom A, H, let's make it atom A. I lied. Let's take atom A and atom B. If I want to identify the attraction between those, if I have a London dispersion force, that attraction is insanely weak. Why is it weak? Because atom A and atom B don't carry charge. They would be neutral. Well, how do they become neutral? There's really two circumstances that we could look at. Say that again?
Lose or gain electrons?
They're neutral, so they can't lose or gain electrons.
Oh, those two.
We could be looking at the atoms in their elemental state. A could, say, be aluminum. And B could be elemental boron. And I could be looking at the attraction between those elements. Those elements are going to have a very weak attraction for each other in their neutral states. Where else could we generate zero charge? Okay. In their elemental state, they're by themselves. So the balance of electrons and protons is identical. But most elements are not found as a pure element. They're found in what? Compounds, which means there's a bond connecting them to something else. Okay? So we have to have some kind of bond over here. Okay? I may not know what A is bonded to, but I know something about that bond because I know this force is weak. I know this force is weak, which means these have to have zero charges. For A to be a zero charge, I also know something about this bond. Atom A is effectively in its elemental state. What is a bond? Sharing of electrons. Okay? So if I have a bond there, atom A must be equally sharing electrons as whatever's connected to it. So I know what the bond is. I know that that bond must be a nonpolar covalent bond. Okay? Because that is the only bond that is going to generate a zero charge for A. So I'm now looking at the interaction between A and B, and just by identifying that strength of the interaction, it being incredibly weak, I now know something about what A is connected to. And I know something about the bond that connects it out. That same thing's going to apply out on the other end. Okay? That's pretty insanely powerful. The same thing can be said the other direction. We started here with what was the force. How does that translate to a bond? In this case, we said that that force was incredibly weak, so we called it a London dispersion force, or just a dispersion force, and that led to a conclusion that our bond had to be nonpolar covalent. Could we have gone the other direction? Let's say I have a hydrogen bonded to an oxygen, and I want to know something about the attractive force. What is the strongest possible force that could be generated tying to that hydrogen? Okay, well, first I would look at the bond. What is the bond that I have between the O and the H? Okay. Hydrogen bonding. There is a hydrogen and there is a bond involving hydrogen. Hydrogen bonding is a force, not a bond. So it is not hydrogen bonding, despite what biologists say. What is the bond? Okay. This is where knowing the definitions of what these things are becomes important. If you don't know the definition, you can't answer the question. You mean I gave you context for what these things were ahead of time? Yes. Yes, it was in the play posit. That's why you should watch that to provide that information. If we look at that bond, it is not a nonpolar covalent because what was nonpolar covalent? Carbon to hydrogen and same to same. I have hydrogen. Is oxygen carbon? No. Is oxygen the same as hydrogen? No, so it's not nonpolar covalent. Is it ionic? How do I know I have an ionic bond? Metal and a nonmetal, or either of those metals? No, which means it's not ionic, it's not nonpolar covalent. What's the only other bond left? Polar covalent. If I have a polar covalent bond, what does that mean my forces could be? Here's that color coding. A polar covalent bond is roughly a green color on our scale. What force would that lead to? That's the point of the color coding. It can now reflect through that. The force that I would expect would be a dipole-dipole force. Right? Could it also be hydrogen bonding? Possibly. Why? It's still green. Okay? To be hydrogen bonding, what must happen? Hydrogen bonding is now another definition. You have to know that definition. To be hydrogen bonding, number one, you have to have a dipole-dipole force. Could we? Yes. So what's the next thing I would need to have? A hydrogen. A hydrogen bonded to nitrogen, oxygen, or fluorine. Okay. Do we have a hydrogen bonded to oxygen, nitrogen, or fluorine?
Yes.
Yes. So we have the potential for hydrogen bonding. Make sense? Those were the strongest attractions we could get. Does that necessarily mean that is the attraction we're going to get? No. Okay? But knowing that bond gives you some information about what it could lead to. That we can use to predict some of the things that I erased on the right to draw this. Yes, Faye?
So even though it's technically hydrogen bonding, we didn't name it as hydrogen bonding in the beginning because it was a force?
So it's coming through what are the steps to achieve the answer. Okay? And that's where the issue is. So the question I asked is what bond is there? And the answer I got was hydrogen bonding from Nadia. Is hydrogen bonding a bond? No. Okay? So the answer to my question was incorrect. Okay? If I had changed the question and said what was the strongest force, now you could say hydrogen bonding. How do you achieve that information of knowing it's hydrogen bonding? Right? That becomes one of the nuances that you have to be careful with when evaluating the strength of those forces. A force is the attraction between two different molecules. Notice in the definition, okay, multiple molecules. Have I defined what the other molecule is yet? No. Okay. Does that mean that red line or red dash line must be hydrogen bonding? No. Okay. So let's go through and draw on a second molecule. What do you think? Is the red dashed line hydrogen bonding?
Yes.
Why?
It's linked to oxygen. Well, it could be both though, right? Because hydrogen bonding is a type of...
To have a dipole-dipole force, we must have a dipole here, do we?
Yes.
We must have a dipole here, do we? Do we have a dipole-dipole? Yes. If we have a dipole-dipole, what should we check for? Do we have a hydrogen physically bonded to nitrogen, oxygen, or fluorine? Do we have a hydrogen physically bonded to oxygen, nitrogen, or fluorine?
Yeah.
Yes. What's the interaction? Hydrogen bonding. How about now?
No.
How do you get a dipole-dipole force?
Can I just say it has to be connected with the carbon as well, depending on what it is?
How do we get a dipole-dipole force? It has nothing to do with carbon per se.
Everything that's not ionic or hydrogen bonding.
You're getting your dipole-dipole force. Remember, the green force came from a green bond. Does the OH have a polar covalent bond? Yes, that's what we walked through. So that will lead to a dipole-dipole. There's literally two words there. Dipole for molecule A, dipole for molecule B. Do we have a dipole for OC?
No.
Okay? The argument you're saying is no, because why? You have carbon. Carbon is irrelevant. Look at the table. Does it say carbon? No. So using carbon as your explanation for why it's not a dipole is irrelevant.
Would it matter if it's double bonded? Like, would that change what it is?
Okay? We're trying to identify if there's a dipole force. To have a dipole force, what must you have? A polar covalent bond. Does that say single, double, or triple? No. So do I care if it's single, double, or triple? No. What I care about is it polar covalent? And William's shaking his head because, yes, he started to shout out some of the answers.
It is.
Okay. How do we know if it's polar covalent? So, and this is, and I know William, but stop. Okay. This is where I think some of you are jumping, well, it had carbon, so it's not polar covalent. Okay. You didn't make that statement. You just said it has carbon, so it's not a dipole-dipole. Okay. So I couldn't evaluate where your break is. Okay. Polar covalent doesn't matter what atoms are connected. Okay. What matters is the difference between them. How do I know I have a polar covalent bond? Damn, that's a hard question. Let's try again. How do I know I have an ionic bond?
No.
Metal and a nonmetal. Is carbon or oxygen a metal? No. So it's not an ionic bond. Yeah? How do I know I have a nonpolar covalent bond? Two nonmetals, which is a fantastic answer. It's also the answer for polar covalent, which means that definition does not allow you to differentiate, which means you can't answer the question. You need a differentiator. How do we know we have a nonpolar covalent bond? You were told rules of thumb from the play posit video that would allow you to differentiate it. If you have the same element bound to the same element, by definition, it's going to be nonpolar covalent. The difference in electronegativity is 0. No poles. Is oxygen the same as carbon? Okay, so rule of thumb 1 is false, so it's not nonpolar covalent. What's rule of thumb number 2? Carbon. Damn, that you guys were right. You're talking about carbon. Carbon, what was the rest of it since I talked over you? Carbon to hydrogen. Is oxygen hydrogen? No. Is this a nonpolar covalent bond? No. So it's not ionic. It's not nonpolar covalent. That must mean it's polar covalent. What were we looking for? To get a dipole-dipole, I had dipole 1 and I needed dipole 2. How do I get the dipole in this bond? What must I have? A polar covalent bond. Does this molecule have a polar covalent bond? Yes. What is the interaction? Dipole-dipole. Since I have a dipole-dipole, I should now ask the next question, which is, is it a hydrogen bonding dipole-dipole? Is there a hydrogen physically bonded to oxygen, nitrogen, or fluorine? Yes, which means that's a hydrogen bonding interaction.
That's the only thing that ruled it out from being dipole-dipole.
Yes, hydrogen bonding is a dipole-dipole force. They're one and the same. Why do we have an extra category for hydrogen bonding? I can give you one word answer for it. Water. Why water interacts and does what it does is largely due to the strength of force between individual water molecules. That force is so incredibly important that what did we do? We gave it its own name to differentiate it from other forces. That's why. Okay, but hydrogen bonding is a dipole-dipole force. This is why in the play posit and as we've talked through it, you first have to establish, do you have a dipole-dipole? Once you have that, then you can move on. Nadia.
So for it to be considered hydrogen bonding, you only need one hydrogen bond?
You only need one hydrogen to be bonded to oxygen, nitrogen, and fluorine. Yes. Okay. So let's play with this a little bit. Do I have a hydrogen bonded to oxygen, nitrogen, or fluorine?
Yeah.
What was that?
Yes.
Yeah, it's still there, right? I didn't change that. So this must be hydrogen bonding.
Are we of nonpolar covalent?
To be hydrogen bonding, you must have the dipole-dipole force. To have the dipole-dipole, you have to have polar covalent and polar covalent. Is the carbon to hydrogen bond polar covalent? No, which means it is a non-polar covalent bond that does not match hydrogen bonding. Okay? That one becomes a lot trickier because now what force should we label that as? Okay? This one was a non-polar covalent bond, which would lead to London dispersion forces. This one was a polar covalent bond, which officially leads to dipole-dipole. The interaction between those. Is it a dipole-dipole? To be a dipole-dipole, I must have two dipoles. I don't, which means it's not dipole-dipole. To be strictly London dispersion, that should be also London dispersion. So what's the interaction that I have there?
Would it be
It's a subtle hint. It's blue. What do I mean blue? Our London dispersion was our purple/black. Dipole was green. We've got some kind of cross hybrid in between. Okay? Dipole dispersion. Okay? And while that sounds weird, yeah, that's pretty much what we do to label it. Okay? Yes?
Why wasn't the OC covalent?
What is a nonpolar covalent? And so this is where we have to be careful. This is one thing I need to be careful on. I'm very, very lazy, right? We've seen that? Okay, we should have gotten like, yeah, you're horribly lazy. Thank you. Acknowledging my failures. What we should be writing above covalent here is nonpolar covalent. Because I'm already specifying polar covalent, by just writing covalent, I now know kind of implicitly that must be nonpolar covalent. So the carbon to oxygen is a covalent bond. Which covalent bond is it? Nonpolar covalent or polar covalent? It's polar covalent. So that's classifying up here in the green. Green means green force. Does that make sense, Faye?
Yeah.
Okay. So cool. How could we use this? Let's just, yeah, fine. We can use this to predict phase transitions. Where do we see phase transitions? Gas to liquid, known as what? Condensation. We could look at solid to liquid, known as melting point. We could look at liquid to gas, known as boiling point. Okay? So we've got access to these terms that you've seen throughout the semester. Being able to look at a formula and predict the boiling point is pretty cool. Okay? Or really be able to predict the relative boiling point in comparison to another structure. It allows us to make some conclusions without having to drill into all of the calculations that we spent all that time in the last unit. Okay? Vapor pressure can be tied to vapor pressure. What is vapor pressure?
Between liquid.
It's the gas above a liquid. Vapor pressure is approximating boiling point, where I have a liquid and a gas. The higher the vapor pressure, the more gas I have. What is that going to mean about its boiling point? It should be lower, because if it was higher, what would happen? If you have a higher boiling point, you have less gas present. A higher boiling point means we aren't at that temperature yet. We'd be at a liquid, not as a gas. Okay, so we can approximate vapor pressure to boiling points. Okay? Viscosity. How do those molecules interact with each other? Honey is very slow and viscous. Why? Because each molecule in honey is grabbing every other molecule. Okay? Because they're holding on to each other, what happens when you try to make them move? They all move together, or they move very slowly because you have to get all of them to move. Okay? You have to get that critical mass. Surface tension, the same idea. It's how those individual molecules are grabbing each other. Viscosity was the entire solution grabbing each other. What's surface tension?
Structure of the cell.
Just the surface molecules grabbing each other. Right? All of those are talking about how two atoms interact with each other and how we would apply that information. Solubility is another big one. What is solubility? How something dissolves. So how two different things mix with each other. Right? If I have a London dispersion force, how well does it mix with itself? Okay, pretty easy. Okay, how strong of an attraction is that? Not strong at all. So very weak attraction. What if I tried to take that London dispersion system and mix it with an ionic substance? Okay? The ionic substance is trying to cancel out the charges, which means the ionic substances are going to align with other ionic substances. Is the London dispersion ionic? Nope, which means it's not going to interact. So I can make simple conclusions from a really basic understanding of the interactions between those particles. And that's massively important. That plays a huge role when you move into reactivity. I can look at a molecule and I can say, this is how I think that molecule is going to react in this particular environment. Right? That's organic chemistry. It's a hardcore application of everything within this. When you move into OChem, you will have to do that application at an advanced level. Right now, you have to do it at a simple level. Okay? We've got 4 questions here. Okay? Ranked in inverse order, difficulty order. So 4 is the easiest, 3 is the next easiest, 2 is the next easiest, 1's the hardest question to answer up here. Okay? You have the context to be able to predict which one has the higher melting point. Should I do one? Yes. Okay. Let's start with 4. Okay. The reason we're not going to start with 1 is so hard it's actually off the scale for our Chem 130 class. Okay? I just want you to be able to recognize and think your way through it. Some of you may already be able to get that answer anyway. That's what's nice about this. Okay, so let's take a look at that last one, okay, with 4. There's varying arguments about what you should be able to interpret out of this. What is that as shown? If I asked you to give me some kind of name about what's in the red box, what could you tell me? We have carbons and hydrogens. Cool. You've interpreted the information there. There's carbons and hydrogens. Yes. Is that it? There's an oxygen. Is there anything else about the information presented there?
We have 2 different kinds of carbon because they're not mixing together. So we have the
Okay. You've got an interesting point here. You have 2 different types of carbons. And you're saying you have 2 different types of carbons because the way they're bonded. So what we're looking at here is a formula, but this formula was a good word you could have said was in the red box, also contains some structural information. Some structural information that sounds an awful lot like Lewis structures. Are you responsible for being able to convert this into a Lewis structure? Yes. Right? At least according to me. Right? And we can talk about some variations off of that in a second. So how does it work? I've got a carbon. What's connected to that carbon? 3 hydrogens. How many bonds or how many electrons should be around carbon? We should have a total of 8 electrons. How many are currently around it? 6, which means there has to be another connection out there. To what? To the very next carbon in the list. That's why it's listed there. What's connected to that carbon?
2 hydrogens.
How many electrons around that carbon? 6, which means
8.
has to have 8. There has to be another connection. Another connection to what? Oxygen. What's that oxygen connected to?
Hydrogen.
Hydrogen. How many electrons are supposed to be around oxygen? 8. How many electrons are around it? What'd you say? Okay, so there's 2 bonds around it, so 4 electrons. It needs to have 8. Are there any more atoms? No. What are those last electrons? Dots. Yes. They are lone pair electrons. You've now just drawn the structure. You are responsible for doing that. In my opinion, it is not a necessary approach, and we'll look at that necessity here in a second. Okay? In our analysis, what we're concerned about is the strongest intermolecular force. Why do I care about the strongest intermolecular force? What's the question being asked? Higher melting point. If you have a melting point that's very high, what are all of those particles doing? They're sticking together. They're sticking together because they have a very strong force holding them to each other. So if we can go through and look at our Lewis structure with all of those bonds, we could now predict the strongest force that could come from that molecule. We could then do that for the other one, and we could then compare those forces. Whichever one was the strongest has the higher melting point. Okay. So when we go through and look at that, we have, starting with red, carbon to hydrogen. What kind of bond is that? What kind of bond is that? That is a non-polar covalent bond. A non-polar covalent bond results in London dispersion forces. We also have carbon to carbon in that purple. What kind of bond is a carbon to carbon? Non-polar covalent, which results in London dispersion forces. What other bonds do we have? We have the OH bond, okay, which I screwed up and didn't color code right. Fuck. Only making it worse. Hopefully I said that quietly enough. OH. What kind of bond is the OH? It is polar covalent. What kind of force is generated from a polar covalent bond? A dipole-dipole. Once I have a dipole-dipole, what should I consider? Do I have hydrogen bonding? Do I have a hydrogen bonded to oxygen, nitrogen, or fluorine? Yes, which means I have hydrogen bonding. In this analysis, what am I looking for? The strongest force. Do I care about the London dispersion forces? No, which means my entire analysis is going to boil down to recognizing that for that molecule, I have hydrogen bonding. How could I recognize that? That gets me there. Okay? So I don't have to draw out the whole structure. I can look at the formula and remember that the formula holds some structural information, and I can see that pairing. Make sense? Next compound.
Same thing with the exception of oxygen.
So we could go through and draw the whole friggin' Lewis structure again. Or focus where those large differences in electronegativity are going to come out. Oxygen's a giant red flag. Oxygen connected to carbon would be polar covalent. Oxygen connected to sodium would be ionic. What kind of interaction is going to be generated from
An ionic force.
an ionic force? Which force is stronger, ionic or hydrogen bonding? Which one of these compounds is going to have the higher melting point?
Wow, that's going to help me on my test actually.
Okay. Next one. 3.
But maybe more than just the same 4 people should be responding this time.
What do you see in 3?
Oxygen, carbon, and hydrogen bond.
Okay. So we see that oxygen. This one becomes trickier. Okay. What is that oxygen connected to?
Carbon.
Carbon. Isn't it also connected to hydrogen? Is the oxygen connected to the hydrogen? No. Read left to right, not right to left. Okay, what does that mean? We have an O to C bond. Try again. An O to C bond is polar covalent. If it is polar covalent, that leads to a dipole-dipole force. Do we have a hydrogen bonded to oxygen, nitrogen, or fluorine? No. This one stops as a dipole-dipole. Next one.
You have the hydrogen.
I have the OH, which means
It's dipole-dipole.
walk through it all the way. Polar covalent, which leads to dipole-dipole, which means
Hydrogen bonding.
I should evaluate hydrogen bonding. I have hydrogen bonding. What is the strongest force I should be identifying for the second one?
Hydrogen bonding.
Hydrogen bonding. What was the strongest force for the first one? Dipole-dipole.
Oh. Yeah.
Yeah, different question. Which one's the stronger force? Which one's the higher melting point? Do two. Do 2 and 1 on your own. Do you want that work left up there?
Yeah.
Okay. We go through and look at 2A. Those are all carbons to hydrogens or carbons to carbons, which are all going to come down to the exact same type of bond, non-polar covalent, which is going to be a London dispersion force. When I move to the next one, I have an O to C bond. That O to C bond is a polar covalent bond, which is going to lead to a dipole-dipole force. Dipole-dipole is stronger than London dispersion, and therefore B is the answer. Let's go ahead and look at 1A. That should look pretty familiar. It's the same as the structure underneath. So we got non-polar covalent bonds leading to London dispersion forces. I just want to address something real quickly with this. We're not just selecting an arbitrary bond. We're selecting the most polar bond that we see, which means you have to look at the entire molecule. For instance, if I jumped to 3A, I could say, well, carbon to hydrogen. Carbon to hydrogen, it is therefore non-polar covalent and thus London dispersion force. It does have that. Is there a stronger force? Yes. So the strength of the force depends at looking through the entire molecule. Okay? Kind of, sort of? Okay. So we take a look at 1B. What do we see? Same deal, carbon to hydrogen, which would be non-polar covalent, which would be London dispersion force. Why does this now become a challenge? They're both the same force. How do we know which one has a higher melting point?
I'm going to say B because it has more bonds in the first.
Okay. So I've heard a couple different answers come out. One, it's got to be A because you made all the other choices B. Bad logic, don't use that. Okay? The other answer I heard was B because there's more bonds in B. What dictates your melting point?
Strongest bond.
The strongest force. So telling me there's more bonds isn't going to fly because to dictate the melting point, it's the force, not the bond. Okay? That force is looking at any two atoms. If I took these two relative spheres and I connected them to each other and looked at the force, what's the force connecting these two? Where's that force going to show up? In between the two atoms, right? For the two things. Only where they contact. Two sheets. Where's the force now? Between them. Is it the same force? Are they both made out of paper? Is it the same force?
One's spread out.
Is an amount changing the force? No. An amount changes our interpretation. There are two aspects. It's labeling it, and now you're quantifying it. Two different things. The force is the same because it's the same paper. The amount of force is different. Why is the amount of force for these two flat pieces of paper different than for the spheres? There's more surface area, which means there's more places to interact. Okay? But that's a sphere and pieces of flat paper. Well, those are clearly both best represented by flat pieces of paper, so my analogy is horrible, right? What if we have a larger piece of paper?
Then you have more areas.
I have more surface area, which means more opportunities for forces to appear. which thereby means more force.
So it's still kind of true though, because there's more carbons linked together.
So,
it takes more to kill
but what are you breaking? And so that's where the analysis comes in.
one carbon to carbon.
You're not breaking a carbon to carbon. What you're breaking are the forces that connect those. So as soon as you start to make the analysis, oh, it's got more bonds, so thereby it's a stronger force, because I have to break more bonds. No, you don't. You aren't breaking any bonds. You're breaking the force. Why has this become such a big deal? Okay? And now that I've heard all sorts about fake news and other things that could be messing with this, allegedly there was a survey that was put out at a Ivy League school where they interviewed their graduate students, first-year graduate students, and said, explain to us what happens when you boil water. And some absurd amount. These are people that have studied chemistry for 4 or 5 years, now getting advanced degrees in chemistry, went through and said that when you boiled water, you got hydrogen gas and oxygen gas. Why are they making that statement? Because they went through and said, when you add that energy, what are you breaking? Bonds. That's not true. When we boil water, we're breaking the force that connects individual water molecules to each other, which means when we go up into the gas phase, I still have water molecules. They're just floating around on their own. Okay? So using language can drastically shift how your brain is going to interpret that information. And so we have to be careful with the language that we use behind it. If your language you are able to encode for yourself to get answers right on a test, that's amazing.
Well, you can
Okay.
identify it being a problem later on.
As long as it doesn't become a problem later on. My goal as a teacher is to point out where it can become a problem and try and address it so that your language is fixed so it doesn't become a problem later on. Make sense? So what's the answer? Which one has more force?
We're going to melt the same temperatures.
They're going to have the same type of force, but 1B has more forces to break. How many of you can break a single strand of spaghetti? How many of you could break 1,000 strands of spaghetti with your hands? Okay. That becomes a lot more difficult. The same logic is applying here. Okay? So just for the sake of completeness, we could circle that.
I got a question. So whenever you're looking at A versus B, like you were talking about Ivy League.
Yep. Whatever that alleged.
Misleading with the breaking of a bond and not the force. Can that be looked at as each one of those CH3, CH2? That's one water molecule, another water molecule. I mean, even though it's kind of not, but so if you're evaporating it, boiling it.
Can I delete everything?
You see what I'm getting at? Like,
I think I see where you're getting at. What we're talking about is that when we look at our forces, oh, I'm going to regret doing this. I don't say that a lot. I've said that like 3 or 4 times
and we're all
this
really
semester.
breaking the carbons first, right?
And here's where it hurts. 5, 6, 1, 2, 3, 4, 5. Can we say those are hydrogens?
Yeah.
Okay. What we're talking about is taking multiple of these molecules and having them interact with each other. Let's take a look at A. There's a potential interaction.
Oh, I got you.
There's another one. There's another one. Let's take a look at B. There's one. There's one. There's one. There's one. There's one. There's one. Okay. The force for any individual is identical. But because there's a larger amount, it changes it. Okay? The analogy I tend to use, which Greg is kind of frowned upon, but I was hoping to avoid, but I'm going to keep coming back to it because you pushed me there. Okay? If I gave you the choice, life or death battle, have you heard, the mountain? Big dude? Yeah. Some people, Game of Thrones. Yeah. Okay. Pick a famous wrestler, a huge, massive dude. The Rock. There we go. That's a better one. Everybody knows The Rock, right? Okay. Fight to the death. You are fighting The Rock, or you're fighting a 2-year-old kid.
The Rock.
Why are you going to take on the kid? He's easier. You can beat him up. The Rock, or a million 2-year-old kids. And for those of you being like, I could take on a million kids. A million is a lot.
Well, they'll win.
Just the weight of their bodies would probably suffocate you.
They have to get united and get on the
Okay. So the amount can make a really big difference. Okay.
Like I say, a grain of sand's not heavy, but if you put a ton of sand.
But if you put a ton of sand in there, that makes a difference. And so that's ultimately what you're looking at, is it's not just the strength of the force. You were very quick, Rock, 2-year-olds. Right? A million 2-year-olds, you're also very quick, but I'm going to argue that your reason for being very quick on that is what is your brain's capacity for the volume of a million. You don't understand what a million is. Okay? And that's your problem.
That's what I'm going to do to the kids, Mike.
Okay? And so that's that line that we have to walk, and that's what we're looking at there. Okay?
I guess just for like you to understand, like what I was thinking is, I was thinking we're actually breaking the CHs apart, not the whole thing.
Yep.
Just one whole thing.
And that becomes the misconception when dealing with boiling points and phase transitions, is we think we're breaking bonds, we're breaking each of those molecules apart. No. We're breaking the molecules away from each other. We're not touching chemical bonds. Okay? And it is that differential that becomes challenging for people to deal with and to manipulate. Okay? That is why you need the bonds and forces, and you need to kind of logic that out in that sequence. Does it get more complicated? And I know, William, you want to keep talking about it, but
No, I was just going to say, drawing all that.
cool. Thanks. Are there other things that affect this? These pieces of paper, balled up, are the exact same size as these pieces of paper. Yet the attractive force was different. What was the difference between these? It's kind of the amounts. The surface area. It's the shape. The shape can affect your melting point and boiling point. Did we really evaluate shape? No. Okay, so it can become a lot more complicated. All I want you to do is to recognize that it can become more complicated. Ultimately, what you are responsible for when it comes to this class is being able to differentiate those. Does the size change? If you go through and look at mass for each of those, they come out pretty darn close to each other. So there is not a mass difference. There's not a size difference. Is the shape different? Nope. That's also not really present there either. Right? So what you're being asked to evaluate here is the easiest level. What are the strongest forces? And now comparing them. Okay? That requires a level of interpretation. Make sense? Okay. With that, we can look at heat versus temperature with phase transitions. We're just going to do this really fast just so that I can say you've seen this. I'm going to add heat, and I'm going to monitor temperature. Okay? And I'm going to start really cold. Let's go ahead and call it 0 Kelvin. As I add heat, what's going to happen to my temperature? It's going to increase. Let's say this is water we're looking at. So it's going to increase. It's going to become hotter, right? Mm-hmm. So, now I'm at 2 Kelvin. Do I notice anything different about my water?
No.
It's still a solid, right? Okay. I continue to add heat until eventually what happens? Starts to melt. At what point? Way to interpret. 273 Kelvin, also known as 32 degrees Fahrenheit or 0 degrees Celsius in non-stupid units. Okay. It's now melting. Okay. Where should my next data point be?
Right.
Okay, we've got a suggestion, go directly to the right. Anybody else want to suggest something else?
Wait, did you stop adding heat?
I'm still adding heat.
Then it still goes straight up.
It still needs to go somewhere to the right. The question is, where should we drop that data point, right? What do you think? We got 3 colors.
Level of
Blue.
Okay, blue says there's no change. So the instant I hit 0 degrees Celsius, what happens to my ice?
naturally melts all one time.
Okay. And this is where we have to be careful with our words. As soon as we hit 0 degrees Celsius, what happens to the ice? All of it becomes a liquid. Is that true? No. What happens? Some of it becomes a liquid. Okay. Well, if some of it becomes a liquid and some of it is still ice, what's happening to the temperature? It has to stay the same. Because if it goes up, I no longer have solid. Okay? If it goes down, I don't have liquid. So what happens is it has to plateau. Eventually, what happens?
Put enough energy into the ice.
Enough energy goes in that all of the solid is now a liquid. Now what happens is I add more heat. Now the temperature will go up until I hit 373 Kelvin or 100 degrees Celsius. And what happens? Another plateau before it starts going up again. Okay? And so what we're trying to do is interpret what's happening at each of those. If you have to move into 151, you will very carefully analyze this. Heat is measured through kilojoules or calories, however you want to measure it. Okay? So there is a heat with a temperature change. There's also a heat change with no temperature change, which means we have 2 different parts of our curve that we'll have to interpret and model when we go through to deal with solving a question about all of the heat transfer behind a particular reaction. Okay? I'm going to leave that for 151. All I want you to be able to do is to say you understand what's going on with this. If we were to add phases on this, that red part would be a solid. And now I'm going to be obnoxious. That purple part would be? There were 2 answers that came out of that. It'll be a liquid and it'll be a liquid and a solid. Depending on which part of the purple curve we're referencing, this would be a liquid, this would be solid liquid. Does that make sense? So when we move up to the next one, we won't make that same mistake again. It starts as liquid gas and then becomes gas. So the next thing that you're referencing is something beyond the scope of the class that's evaluating other aspects. What you're trying to get at is kind of auto-ignition or other aspects behind that. That's, I don't want to deal with that. Okay? Because it's also going to bring in things like pressure. Okay? Vapor pressure. Based on intermolecular attraction, which of the following liquids has the highest vapor pressure? What did I say vapor pressure approximates? A high vapor pressure means what? Melting point isn't going to be useful because melting point is which? Solid to liquid. And vapor pressure is about gases. So a high vapor pressure is going to be related to a boiling point. What should the boiling point be? High or low?
Low.
A low boiling point means lots of gas. A lot of gas means a high pressure. Okay? That right out of the gate is your first awesome interpretation. That is a phenomenal thing to try and translate and do. What's extra fun about that is notice that they are inverses of each other. So people commonly screw that up. To get a low boiling point, what would I need? I know where you're going with that, but that's too far out. Okay? Our phases are dictated based off of forces. So a low boiling point means a weak force. Our weakest force would be a London dispersion force. Okay? How do I know I have a weak London dispersion force? If that's coming from a non-polar covalent bond, okay? Which is really the example, it's actually going to come from what type of bond? So, for reference, we said a weak force was London dispersion. Okay? You're giving me the example. It needs to be a non-polar covalent bond as the example. What's the adjective describing the bond? It must be a strong bond. When we go through and look at the question, we're being given formulas or some bond structural information. You're being asked to reverse this process. How many logical steps did you have to move through? 1, 2, 3. That's a lot of processing. Notice up, down, down. So at least that one was nice and straightforward. Then strong is back up. So we've got a lot of opposites within that can confuse your analysis process. This is why writing that down can help you solve it. Writing it down. Kind of like drafts. Kind of like paper homework. Okay? That writing process can improve the odds of you getting it right. If you don't write that down with all of the inverses in there, you'll end up potentially picking the wrong answer. Okay? So now we should go through and try and decide what bonds do we see in there. We want strong bonds. So we could go through and look at A, and B, and C, and D, and E. And what do you notice in all of those? They all have that bond. Right? So what are we actually being asked to look at? The rest of the molecule. Okay? So what do we see in answer choice A? Carbon and oxygen and oxygen and hydrogen. We heard a suggestion for the hydrogen bonding, which means you ignored the carbon and oxygen because the oxygen to hydrogen is going to get you a stronger force, hydrogen bonding. We move to answer choice B, and what do we see in there? If we deleted CH3, we could delete CH2. If we delete CH2, we could delete CH2. So we delete the entire molecule. What's the strongest force in nothing?
Nothing.
A very, very weak force. Okay? So B's looking like a solid answer. When we look at C, what do we see? That oxygen to carbon, which is a polar covalent bond, which leads to a dipole-dipole force. D. This one gets a bit harder to tie, but you're tying the carbon to the chlorine. That was a horrible way to do it. Okay, but you're tying the carbon to the chlorine, which is, that's a polar covalent bond, because there's no metal, which then means dipole-dipole. We move to the next one. Sulfur to carbon, which is polar covalent, which will lead to a dipole-dipole force. Which of those had the weakest force? The one we erased, because there's literally nothing there to have a force. And that weakest force was what? A London dispersion force. Okay? Which means our answer for this is B. Kind of, sort of? Logical thought behind how we move through those. You have to be able to interpret the formulas to get to bonds, to get to forces, to get to boiling points, to get to vapor pressures. All of those steps are there. If you do it in your head, great. Okay? And get it right. Okay? If you do it on paper, better, because you'll get it right. Make sense? Okay. Solubility. Solubility is a like dissolves like. Okay? So, two kind of definitions. Well, we're not going to worry about that. There's definitions up there. You can read them. There's a rule of thumb, like dissolves like. I personally don't like that rule because it doesn't clearly enunciate what the like is. Like what dissolves like what? What's the what? It's a force. What we're being asked to do when we're talking about solubility is say, are the forces similar between the molecules? If they are similar, what will they do? They will mix, thereby dissolving, getting us soluble or miscible. Let's take a look at water and whatever that is. I'll accept that. Okay? What do we think? What force do we see in water? We have a polar covalent bond in the hydrogen to oxygen bond, which leads to a dipole-dipole force, which leads to hydrogen bonding because we have a hydrogen bonded to oxygen, nitrogen, or fluorine. Move to the next molecule. Oh, well, that's London dispersion, so they shouldn't mix. Just like with melting points, you need to identify the strongest force. O to H, polar covalent, dipole-dipole, hydrogen bonding. Is hydrogen bonding similar to hydrogen bonding? Yes. Should those two mix? Yes. When you're old enough, go to a bar, you'll prove it. Next one. H2O, CH3, CH2, CH3. H2O has hydrogen bonding. CH3, CH2, CH3. All London dispersion. Is hydrogen bonding same as London dispersion? No, which means don't mix. It's as simple as that. Right? Are there weird cases? Yes. If we looked at this based off of colors. Water, we have hydrogen bonding, so green. The propane, CH3, CH2, CH3, we have London dispersion, so black. Is green the same color as black? No. Is green the same color as lighter green? That'll work.
No.
Kinda. Does that mean it should dissolve or not? Kinda, yeah. Okay. You will find gray areas that are more difficult to interpret. Those more difficult to interpret gray areas show up in future classes, not this class. Okay? So identify your force. Are the forces the same? Then they should mix. Okay? The language, miscibility, solubility are important terms. You should evaluate those. What is the opposite of soluble? Insoluble. Use the English language. What is the opposite of miscible? Immiscible. I am miscible. I'm going to say use the English language, but I don't really know that one.
Probably.
No, it's immiscible. Okay. Water insolubility we already talked about, but what we can do is look at, well, a slightly different case. Okay? Like dissolves like, which of the following liquids is miscible with water? So we're being asked to compare solubility. Like dissolves like. Like force A dissolves like force B. You need two things. One of those things is one of your answer choices. What's the other thing? To evaluate, we need to look at structures, right? Where do you see structures in the question? In the formulas. Okay? Which formula? Whichever one's the correct answer. So there's 4 wrong formulas. What's the other formula you have to compare it to? you have to be careful with the question. It's telling you water, you are required to know H2O. That's a small interpretive leap that a lot of people will miss. The forces for water are forces, hydrogen bonding. So what we would have to do is find which one was hydrogen bonding. Glycerin, our answer is D. Make sense? Okay. Just want to talk through real quickly what we're going to be doing on Thursday. On Thursday, we're going to run through some definitions on acids and bases. Lots of definitions on acids and bases. Okay, and then we will look at, come on, work with me here, equilibrium and some analogies that we can work with equilibrium. These analogies are awesome for the record. Okay, we'll talk about some things with rate. We'll look back at equilibrium versus acids and pH real quickly, and then we'll talk about electrolytes. And then we get the black screen of death. I said like completion was a good one. Awesomeness. Okay, because we would then be done. I would recommend that you show up with questions. I wanted to talk through all of that stuff today and just didn't get to do it. So we'll try and go really fast through that on Thursday so that we can start answering questions about the practice exam.